Alright, welcome to the Crazy Hat Chemist. This is the 6th video in the series of 16 dealing with gases. Today we're going to be talking about Boyle's Law. So here we go. Boyle's Law is at constant temperature. So that is a fixed mass of gas is inversely proportional to the pressure. So volume and pressure are inversely proportional. And you can clearly see that hopefully on this graph that I have here for you. As the x-axis, as the pressure of the gas increases, then you should see that the volume is decreasing. So we get this relationship with Boyle's Law at constant temperature of a gas. That is, volume is proportional to 1 over pressure. So that is an inverse relationship. And therefore, we get this equation mathematically. So P1 times V1 equals P2 V2. This is very similar to the combined gas law in the previous video, where we had P1 V1 over T1 is equal to P2 V2 over T2. But with constant temperature, we don't have to have the temperature in there. So here's a little bit of Boyle's trivia. He was a British scientist, number one. He was the first one to carry out experiments in which one variable was systematically changed to determine the effect of another variable. That's critical in how we do science today. Breathing is an application of Boyle's Law, and same thing with scuba divers when they experience the bends. That is also an application of Boyle's Law. So one of the things that we want you to do as chemists when you're doing math problems is we want you to do a prediction. We want you to make a prediction, okay? And in this example, okay, temperature is being held constant. So you can see here on this little piece of wood, I have volume, temperature, and pressure. And so we are going to be rotating at the place where it is being held constant. And in this case, it is temperature dealing with Boyle's Law. So if you can look at those arrows there, they rotate, and that is the pressure is going up, the volume is going down. So the pressure will go up, the volume will go down. Alternatively, if the pressure goes down, the volume will go up. And take a look at these set of arrows here and look at the rotation. We're rotating again at where the temperature is. So here's our rotation of that. So it's an inverse relationship. Volume goes up, pressure goes down. Pressure goes up, volume goes down. So let's do an example of this. A gas occupies a volume of 0.86 liters at 1.45 bar. At what pressure in millimeters of mercury will the volume be 660 milliliters? So what we're going to do is we're going to convert our volume this time in liters to milliliters. If you remember on the combined gas law problem, I converted the milliliters into liters. This time I'm going to do the opposite. So 0.86 liters has 2 significant figures, and I'm maintaining 2 significant figures. With the 860 milliliters, there is no decimal in that number. And if you notice, this is the combined gas law equation here, where I have the pressure, the volume, and the temperature, but I've highlighted the 2 temperatures, because with Boyle's Law, there is no temperature. There is no temperature mentioned in this problem, and even though it does not say that temperature is constant, it is assumed that temperature is constant if it is not mentioned. So we're going to get rid of the 2 temperatures there, and then we're just going to have the P1 V1 equals P2 V2. Remember, I had this before, and we're going to make a prediction. We are rotating at the temperature, okay? And then we have P1 V1 equals P2 V2. Okay, and you should see that I have 860 milliliters at 1.45 bar and 660 milliliters. So what's happening to the volume? The volume is going down, therefore the pressure will go up. So I've rearranged the equation to solve for P2. That's V1 times P1 over V2. I'm going to plug in the numbers here. My milliliters cancels out. I'm going to look at the number of significant figures that I have on each of these numbers here. I have 3 significant figures in the 1.45 bar, 2 significant figures in the 860, and 3 significant figures in the 660 because there's a decimal after the 0, and trailing zeros count with the decimal in the number. Least number of significant figures I have is 2. And you should see that our prediction where the temperature was being held constant is true. So that is, the volume is going down, therefore the pressure is going up. That is, 1.9 bar is greater than the 1.45 bar. But the question was asking for at what pressure in millimeters of mercury. So what we're going to do now is convert the bar into millimeters of mercury. And here I have that here. Bar is being converted to millimeters of mercury. The 1.9 bar has two significant figures, and the 760 has infinite, and the 1.013 bar has infinite, and now I have 1400 millimeters of mercury. There's no decimal because there's two significant figures, and that's my answer in millimeters of mercury. All right, so this was the 6th video of Boyle's Law in the series of 16. Next time, you're going to be looking for Charles' Law. And Charles' Law is video number 7. I hope you have a great day, and I will see you for Charles' Law. Bye now.